Okay, this is the second video about work and energy. We're going to be looking at the work done by gravity, and then also the work done by a variable force. Now gravity is just like any other force, but it shows up a lot, so we're going to spend some time on it specifically. Remember that the work done by a force is equal to that force dotted into the displacement. And for gravity, the force is mg, and so d is the displacement, and then this angle phi is the angle between the gravitational force, which points downward, and the displacement. Now one thing about this is that if an object is moving upward, gravity is doing negative work. It's taking energy away from the object. And that means if you lift an object, you are doing positive work because the upward force that you exert is in the same direction as its displacement, while gravity does negative work. And so that means you are putting energy into the object and gravity is taking it away, and the result is if you're lifting it at constant speed, the kinetic energy of the object is not changing. So here's an example. In order to throw a 500-gram ball in the air, you exert a vertical force of 25 newtons over a distance of 15 centimeters. We want to find the speed of the ball after it leaves your hand. Well, we're asked about speed, and this has something to do with energy, so we're going to use the work-energy theorem, where net work equals the change in the kinetic energy, and net work means the work done by gravity plus the work done by you, and the change in the kinetic energy, because it starts from rest, is the final kinetic energy, or 1/2 mv squared. We know m, and we need to find the work. So moving over here, the work done by gravity is equal to the force of gravity, which is 0.5 kilograms times 9.8 newtons per kilogram gravitational field, times the distance it travels, which is 0.15 meters. But since gravity is pointing the opposite direction of the ball's displacement, we have to make the angle between the force and displacement 180, which is -1, and we find that the work done by gravity is 0.74 joules. The work that you do, on the other hand, is the force that you exert, 25 newtons, times 0.15 meters, times the cosine of 0, which is 1, because you're exerting an upward force and the displacement is also upward. And that works out to be 3.75 joules. So the idea here is that you are adding 3.75 joules of energy to the ball. And gravity is taking 0.74 of that away, which means that the net change in energy is 3 joules. And we can solve the equation and find that the speed of the ball works out to be about 3.5 meters per second. Moving on, we also need to find the work done by a variable force. This is where it gets a little bit complicated. Now, let's say that you have a particle that's free to move along the x-axis, and it's under the influence of a force directed along the x-axis. Basically what that means is it's only moving in one direction, and the force is always going to be either in the direction of motion or opposite the direction of motion. It's not ever going to be at an angle, so that makes this a little bit easier. And this force has a changing magnitude, meaning at different locations, the force has different strengths. So we'll make a graph of force versus position. And let's say that it looks something like that. And we're going to move some particle from initial position xi to final position xf. We want to know how much work the force does, not how much work we do, but how much work the force does. In this case, a positive force means that it points in the positive x direction. Negative force means it points in the negative x direction. Let's think about what's going on. In order to get from initial position to final position, this particle has to go through every position in between. So we've got a whole series of little tiny delta x's. And if we look at that first one, the force is roughly constant over that little rectangle. And so the height of the rectangle is the force. The width of the rectangle is delta x. And so if we calculate F dot delta x, we get the area of that rectangle. And then it goes through each of those subsequent delta x's. So we need to sum up all the F delta x's. But since you know calculus, and, well, before we get to calculus, we'll say that the work done is equal to the area under the curve. So this whole area here. Keeping in mind that the area that is below the x-axis is negative work, because at that point the force has switched directions and it's slowing it down. And the way we write this mathematically is this is an integral. That the work done by this force is the integral from the initial position to the final position, definite integral, times F dx. Where F is the force, this is the formula you would use if you had a mathematical expression for the force. So here's an example of how you'd use this. And the most common sort of variable force that we're going to have is a spring force. And the force of the spring is given by negative kx. X is displacement from equilibrium. So if we graph this, the graph looks like that. The force is always in the negative direction, and the slope is negative k, where k is the spring constant. And we want to know how much work the spring does when you stretch it from a displacement of 3 centimeters to 10 centimeters. So 3 centimeters to 10 centimeters. We know that it's the area under that curve, but since this is a calculus-based class, we're going to do it algebraically. You could do it by finding the area of that trapezoid. It wouldn't be too terribly difficult. But one thing we can tell is that the spring is going to be doing negative work. You're doing positive work. You're adding energy. If the spring wasn't there, you'd be making this particle speed up. But as it is, the spring is taking energy away, so it does negative work. And to find the work, we have to get the integral from initial to final position of f dx. So we get negative k xi to xf x dx. Now that integral is easy to do. It's just 1/2 x squared. And then we have to evaluate it at 3 centimeters and 10 centimeters. But let's keep this in meters. And so we have negative 1/2, k is 110 newtons per meter. And so we have 0.1 meters squared minus 0.03 meters squared. Put this in your calculator, or you could have put everything in your calculator at this point. You get that you have the spring has done negative 0.5 joules of work. And that is the work done by the spring. For tomorrow, I'm going to be checking questions 4 and 5 from chapter 7.